Okay, so chemical equivalence and the chemical environment. So the point of this is to determine each unique environment each atom is in. Now, the atoms we're looking at is generally uh, carbon or hydrogen. For this one, we're going to be doing hydrogens. So the point of determining this as well is going to help us with our HNMR spectrums, which we use in lab to determine the identity of an unknown compound. You place a little sample on a tray, and the computer gives you a graph or like a chart, and it has different signals on it. So let's go ahead and start looking at some different chemical environments and some examples. So say we have a molecule. Oops. Say we have a molecule like this one. What are our different chemical environments? So, well, we know that each of these are going to be, the two hydrogens, that's the same, because they can rotate all around that carbon, they're the same. But let's start with this one here. What are these all affected by? It's affected by this chlorine, it's affected by these. That would be one signal there. Now this one is a little bit farther away from this chlorine. You see it's two spaces away from that, really, and hydrogens. That's going to be a different signal as this one, whereas this one was only one space away. And this one, again, is even farther away, so that would be yet another signal. So this one would be 3 signals. This stuff just takes a little bit of practice and getting used to. It's really not that hard. Okay, let's just look at another example. Okay, so this one we can see, we can go ahead and just label that first one. This is in its own chemical environment. Now this one here, we can see it's directly attached to the bromine, whereas this one was not. So we know that this one could be this one is a different environment from that one. Now this last group here, it's right next to this group here, and then it's right next to this one here, just the same as this A group is right next to this one, and then right next to the bromine. This is the same chemical environment as this first one here. They're equally apart from each other. Now you can look for symmetry like that. It generally helps pick out the same chemical environments like that. And this bromine on a single bond, in reality, this thing is rotating super fast all around this carbon atom here. So if that's confusing you with the symmetry, it's up here as well. It's up here and it's down here. It's moving all over the place. So you could split it right down the middle. Those are the same environments. Let's try another one. Okay, so let's just go ahead and write our first signal there, A. It's 1 away from the oxygen here. Now this one, again, it's only 1 away from that oxygen, this other one. This is the same signal. Again, you could draw your line of symmetry right down the middle. They're both equally spaced apart from that. They're going to be the exact same chemical environment. Or this was one signal. Okay, let's try this one. Okay, so we have a nitrobenzene here. Now we know with these groups, these hydrogens are actually implied. We know they're there, we just don't draw them out in the skeletal structure like this. They have to be there for the carbons to be neutral, sp3 hybridized. Okay, so let's see. This nitro group is affecting, we can see these are going to be in the same environment. It's affecting both of these equally. They're both just one well, I mean, you could say 2 away, 1, 2, like that. That's one signal. Now these here, you can see another line. Those are going to be in the same signal. They're both equally apart. But, you know, it's farther away from that A one, so it's a unique signal. And then this one is farther away as well from all the others. That is another unique signal. 3 signals for that. Okay, let's try this. Okay, so we can see this hydrogen here, it's, you know, it's 1 away from there, it's 1 away from there. That's its end signal. Now let's look at this hydrogen. It's, yeah, it can't rotate, so it's not going to be the same because that double bond, but it's 1 away from a carbon, and then, you know, you could say 2 away from a chlorine, like that. And then this, it's affected the same amount as that one. You could draw a line of symmetry like this, actually. Those are going to be the same signal. Okay, let's just try a few more here. Okay, once again, we can just go and draw in our implied hydrogens. What do we have? Okay, this is its own signal right there. You see that these, you know, they're being affected over here, they're being affected by these, and affected by these, both equally. They're both the same distance apart from that. So these are in the same environment. Whereas these ones here, see, these are closer to this OCH3 group, whereas this is just a CH3 group. You know, so this is only, you know, 1, 2 away, whereas these ones were 1, 2, 3 away. So that's a third signal. And then here would be that CH3 is obviously it's only 1 away from the oxygen. That would be the 4th signal in this case. Okay, the last one. Okay, so we can see this one here. It's 1 away from the bromine, and it's 1 away from CH2 like this, 2 away from this other bromine. Whereas this one, 1 away from a CH2, same as this one, and it's 1 away from a bromine, 2 away from this one. This is the same signal again. We could draw symmetry just like that. So that would be one signal. And just to keep in mind, sometimes it can help. You can draw these out like this. Sometimes this just helps to visualize it. And you know, that might just be more obvious to you that these, you know, are both the same. They're equally apart from these and from this whole group here. It's going to be the same on both sides. Okay, so there is chemical equivalence.